For the last part of the first chapter, we will be looking at certain tenets of rational choice. Right? Now, here the notion of choice function will be defined in a slightly different sense. Right? Here, we will define a choice function simply as C of S. So, from a set S, you choose the quote-unquote best element. That's what a choice function is defined here as. Till now, we've been using the choice function as a function to choose from set S using a binary relation. Here we generalize it in order to talk about certain properties that a choice function has. So this is a general way to denote a choice function. Of course, more general, right? Of course, this includes a situation where you use binary relations to make this choice. As we will see, that when you use binary relations, certain properties of choice functions can and cannot be satisfied. So now the notion of rational choice comes in here, right? When you have a choice function in anything, social choice theory, consumer choice theory, whatever, you would expect certain things to be followed by your choice function, right? Certain properties of rationality. So here we have two properties which are used. The first is property alpha. Property alpha is very simple. Property alpha means that if X belongs to S1, which is a subset of S2, then if X belongs to the choice set of S2, by whatever means you make this choice, binary relation or otherwise, then X should also belong to the choice set. This is a very basic property. What it means is that if X is a best element of this big set, right, then if we take a smaller set and X is in that set as well, it should be a best element of that set as well. Right? So to take an example, this means that the best movie in the world is also the best American movie, if it is an American. So this is the first property you expect a rational choice function to have. Another property which we are discussing here is property beta. No prizes for guessing. This property is slightly more complicated. It says that if X comma Y belong to the choice set of S1 and S1 is a subset of S2, then X2 should also belong. Then if X1 belongs to the choice set of this larger set S2, right, that is the same as saying Y also belongs to the choice set of S2. What does it mean? Let's take an example. Continuing the movie analogy, let's say Fast and Furious 6 and I don't know, Casino are the best American movies. Then, if Fast and Furious 6 is the best global movie, Casino must also be the best, and vice versa. Right? These are two properties which you want some choice function to have. Right? Yeah. Now, when we make these, so these properties were for any choice function, no matter how you make that choice, that is not fair. These are properties you want your choice function to have. Now we will see whether when we use binary relations to make choices, these properties are satisfied. So lemma 1 star n. I'm going to use the number of the lemma from now on corresponding to the right. So if CS are right, generated by, if this choice function is generated by a binary relation, right? So relation R, binary relation R satisfies alpha, but not necessarily beta. How do we check that it satisfies alpha? Let me use a different color. Suppose X belongs to the choice set of S2 and S1 subset S2. Now take Y belongs to S1, which implies Y belongs to S2, which implies XRY, right? Which implies X belongs to S2. Very simple, right? Now to use a counter example to show that it does not necessarily satisfy beta. So this was part B. To show that it does not necessarily satisfy beta, XIY, XPZ, ZY, right? Check that this triplet does not satisfy property beta, right? Another very simple way to not satisfy property beta is if when you go to the larger set, there is an element with which you have no relation, neither R nor the other, neither it's not at least as good as the other one, and the other one is not not at least as good as this, because there's no reason R should be complete, right? Here we are dealing with a general binary relation. So the other way this can happen is, suppose X comma Y, I'm just going to sketch it, and X comma Y were the choice set of S1, S1 subset S2. X belongs to the choice set of S2, right? But there belongs, Z belongs to S2, right? And does not belong to S1 such that not Y and Z, right? Then also we will have the same. Okay. So now, when can we say that a binary relation does satisfy? We change the color, yeah. When can we say that a binary relation will generate a choice function that satisfies property beta? It turns out this is something to do with PI transitivity, which we have already shown earlier, right? Transitivity. This holds, of course, for a quasi-order. Here we are not assuming quasi-order, we are merely assuming PI transitivity. So PI transitivity, just as a reminder, okay. So let's see why. Right. So we use lemma. C of SR is beta satisfying if and only if R is PI transitive. Right? So first only take this XPY by Z, right? And not PI transitive. Check that beta is not satisfied. Done. Right. Now, for the if part, let us remember one thing. Whatever, whether R is PI transitive, not PI transitive, R must be reflexive and complete in order to generate a choice function in the first place. So so that is presupposed, right? Okay, so let's prove this. So suppose x comma y belong to the choice set of S1. S1 is a subset of S2. Now suppose x belongs to the choice set of S2 and y does not belong to the choice set of S2. Right? Now this implies, right? So we are going to prove by contradiction. This implies that there exists Z belongs to S2 such that Z P Y. Why is this true? This is something that can be left as an exercise. But this implies, right, that ZPY and since we have ZPY and we have YIX, which in turn implies ZPX, which in turn implies X does not belong to C of S2. Contradiction. Okay. Now, something which becomes very relevant here is how did this come together? This gives you a side property, which is that if X comma Y belong to C of SR, right, then X and Y. Why is this true? Very simple. XRX has to be true. XRY has to be true. YRX has to be true since both of them belong. So this is not important. XRY has to be true. YRX has to be true. And so XR. Right? These have to be true because, well, that's the definition of a best X. Now this leads us in an interesting direction vis-a-vis PI transitivity, PP transitivity, and all that. And we will see how they are interrelated. This is again a very interesting part of this first chapter. As we continue to assemble tools which will help us prove more and more powerful results. So lemma 1O, part A is trivial. Right? It says that PP and PI are independent of each other. So if one exists, the other may not exist. So there's nothing you can say about one if we don't know about the other. The second lemma is more interesting. PP and PI implies transitivity given completeness. Right? So if R is complete, and we know it is PP transitive and PI transitive, then it must be fully transitive. How do we prove this? Very simple. Let's say, again, let's use contradiction. Say we have XR, YRs, and not Z, not XRZ, which implies ZPY, because of ZPX by completeness. Now, we have ZX. XRY, we know. If XPY, right, then by PP, you have ZPY. Right? And if XIY, then by PI, you have ZPY. But we know, right? So this is a contradiction. Because if YRZ is true, ZPY can be true. The next lemma, which is one of the final lemmas of the first chapter, is that if R generates a choice function, PI implies R is an ordering. But of course, an ordering is a complete, reflexive, and transitive binary relation. Now, this problem can be rephrased as saying R is transitive. Why? Because the moment R generates a choice function, it is already complete and reflexive. Right? So we just have to prove that R is transitive. But from the previous lemma, we know that R is going to be transitive if it is P transitive, given PPI transitivity holds, right? So this is further equivalent to saying R is transitive. So you see how using given information in prior lemmas, we have broken down R is an ordering to R is PP transitive, which is a much weaker condition. So suppose R is not PP, right? Therefore, there exists x, y, z such that x, p, y, y, p, z, and z are x. Right? Now, we know that if R generates a choice function, R has to be acyclical, right? So, x, p, y, and y, p, z implies x, r, z by acyclicalness, right? Therefore, x, I, z, you can say. But then, x, I, z, sorry, y, p, z, and z, I, x, right, together imply y, p, x, which is not true, which is false, right? This step occurs by pi. Therefore, R is PP, right? Which implies R is transitive, which implies R is, right? Very simple stuff, right? So now lemma 1 star q, which is given in the book, is fairly trivial. It's not worth mentioning here. I think you can read it up yourself. Lemma 1 star R is an interesting one. It says that if R is complete, Pi and IP are implied by each other. Pi implies II, and PP and II imply PI. Right? Now, there's a diagram given in the book, which is very interesting indeed. We will not be drawing that diagram here, but it's very simple, right? So, in order to be transitive, you need all four kinds of transitivity to hold: PP, PI, IP, and II. So given these relations which we just wrote down, the proofs of these are very simple. I think we can prove one of them just for illustration. Let's prove the first one. I think this proof is not given in the book. Let's prove this. I will prove it only one. Right? So suppose we have PI. Suppose I have xi by yp z. Right? I want xpz. Suppose right, it is not so. Right? So two cases are possible. Xi z. Why can this not happen? Because then ypz and xi z imply, right? Ypz and zix would imply ypx, which is not true. So this is not possible. The other possibility is zpx. Right? What is the problem with this? Zpx, sorry, imply zpy. Not true. We do make these results by pi. And therefore, xpz must be true. And we are done. In a similar manner, you can do the rest of the proofs. Now, what this series of results gives us is very interesting. It tells you that if I have PP and II, then I have PI. But we know PI and PP together give me full transitivity. Similarly, if I have PI and let's say PI and PP, this will automatically give me II and I. and so on. This is given in the book in a nice manner. You can just check out the diagram. It's not very relevant. I think it's fairly easy. This is one thing. The second diagram which the book gives, and we will draw, is this. Okay. This is the second diagram. What does this mean? This diagram means that if we know that the choice function has been generated by R, then transitivity is the same as saying that we are PI transitive. Why? Because we know that given a choice function, PI transitivity implies PP transitivity, which implies T, right? And vice versa. T always implies PI in any case, whether or not the choice function exists. And we also proved that Pi and beta, property beta, imply each other given that a choice function exists. This is the basic summary of the results in the final part of the chapter. Thank you very much. With that, we end chapter 1. The next video, we will be starting off with chapter 2, which deals with, I think, Pareto optimality, unanimity, and also some compensation tests.